Hi everyone. So we're going to be talking today about how to use Laplace transforms with piecewise defined functions. It turns out that in many applications of linear differential equations that we run into these piecewise continuous functions, and especially as forcing functions, right? So if you think about spring systems or electrical systems, or those kinds of things that we model with second order linear equations, sometimes you'll be applying a force, and then at a certain time point you might want to turn it off or change it in some way. And if we're going to solve systems like that and understand how they behave, then we need to know how to take Laplace transforms of those kinds of functions. So thankfully we have all the tools already that we need, and the way that we're going to do it is with our new friend, this Heaviside step function. So h of t is the function that is 0 for t less than 0 and 1 for t greater than or equal to 0. And if you'll recall, the Laplace transform of a function like that, of h of t, is equal to 1 over s for s greater than 0. And this is the same as the Laplace transform of 1, because on the interval from t greater than or equal to 0, it's the same as the function 1. Right? But when we shift it over, it changes a little bit. We have the shifted Heaviside function. It's been moved over to the right by alpha units. Then it goes 0 up to alpha, and then at alpha it jumps up to 1. And this function has a Laplace transform. This guy, alpha, equal to e to the minus alpha s over s. And again, that's for s greater than 0. So with the help of these kinds of functions, we can figure out how to take the Laplace transforms of piecewise defined functions. Let's see how that works with a few examples. So start with a piecewise defined function, f of t equal to 2 from 0 to 3, and for 0 from 3 onwards. Now, of course, you can find the Laplace transform of this kind of thing just by taking the integral, using the definition of the Laplace transform. So you could say, oh, well, this is going to be the integral from 0 to infinity of f of t dt. Sorry, not f of t dt, but f of t times e to the minus st dt. And you can calculate. So you can even say, oh, look, well, it's going to be the integral from 0 to 3, because everything else is 0, of 2 e to the minus st dt. And you can proceed in that way. No problem. That's fine. But as these functions get more involved and the things on the right-hand side are not just constants, this gets increasingly more complicated to do and more tiresome to have to go through. So it'd be nice to have something a little bit slicker that we can do to deal with these kinds of functions. And we have this kind of thing. So the first thing we want to do is express the function that we have using Heaviside functions, express it using a single formula that doesn't have these branches like the standard piecewise continuous function does. So let's think about the graph of this function. So this is a function that is equal to 2 for the first 3 units, and then it's equal to 0 afterwards. So the graph of this function would look like it'd be 0 here, and it would be 2, so it's 2 there, and then all the way over it's 2, and then it jumps down to 0, and it's 0 from then on out. So what you can think about this, and if you want to rewrite it in terms of Heaviside functions, is that it's equal to 1 or 2 times 1 all this way, and then you have to subtract that out and then continue, right? So if you're going to write that in terms of step functions that are only going up, you do it the following way. This f of t is equal to h of t minus, 2h of t minus 2h of t minus 3. So from 0 to 3, it's going to be 2 times 1 minus 2 times 0. And then beyond 3, it's going to be 2 times 1 minus 2 times 1. So 0. That works out. That works out exactly the way we want it to. So, therefore, the Laplace transform of f of t will be equal to 2 times the Laplace transform of h of t minus 2 times the Laplace transform of h of t minus 3. And that will be, therefore, 2 over s minus 2e to the minus 3t over s. And so just a little bit faster this way. And it turns out to be very useful for bigger, more complicated functions that we have to deal with. So this is the system. This is the way that we're going to want to go forward. Let's try with something a little bit more complicated. So here we want to find the Laplace transform of the function f of x is equal to sine t from 0 to 2 pi and then 0 onwards. So again, just for orientation purposes, let's think about what the graph of this would look like. So pi over 2, pi, 3 pi over 2, and 2 pi, and then 5 pi over 2, etc. 1, minus 1. So it goes here, 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 here. All right, so our graph looks like this. Oop. And at 2 pi it stops, and it goes 0. So in fact, that last point just doesn't happen. So this function does one full period of sine and then disappears. Then it's just 0 after that. Now, that we could just say, okay, well, let me just figure out this integral. You'd have to integrate sine t times e to the minus st from 0 to 2 pi. That is not something I'm interested in doing at this moment. So we have a little bit of a different way of doing this. So let's rewrite f of t as a function, a single function using Heaviside functions. So at the beginning here, it's definitely going to be equal to 1 times sine of t. So we're going to go h of t times sine t. And then we have to subtract off. After that, whatever was happening, this sine t that's happening has to be subtracted away. So from 2 pi onwards, we have to multiply by sine of t there. Those are going to cancel out afterwards, but in the beginning, we're going to have that full cycle happening. All right, so now it's just a question of can we find the Laplace transform of this? And in order to do that, one useful formula is going to be one of our shift theorems, which says that the Laplace transform of f of t minus alpha times h of t minus alpha is equal to e to the minus alpha s times f of s. So if you know the Laplace transform of a function, and now you've just shifted that function, you're in business. Now, one thing that's nice to note here is that we can do a little bit of cleanup. We want to see these things matching, t minus alpha, t minus alpha. Here we have t minus 2 pi. It would be nice if we had sine of t minus 2 pi. But since sine is 2 pi periodic, we can just change it to sine of t minus 2 pi. It's the same function. F of t is equal to h of t. Well, let's write it so it matches up with the form of the formula. F of t is equal to sine of t h of t minus sine of t minus 2 pi, which is the same as sine of t, times h of t minus 2 pi. All right, so to find f of s, we take the inverse Laplace transform of sine t h of t minus the inverse Laplace transform of sine of t minus 2 pi h of t minus 2 pi. What does that get us? Well, for the first one, it's just going to be 1 over s squared plus 1. For the second one, so we get minus, then we have to shift everything over. So this shift theorem tells us it's e to the minus 2 pi s over s squared plus 1. There we have it. That is the Laplace transform. Okay, let's try just try going with a different one. Again, another example. This time we're going to have a gap at the beginning. We're going to go 0 for a while, and then it will be the function t. All right, so let's take a look again. Always useful to have just an idea of what the graph looks like. 1, 2. For this interval, nothing is going to happen. And then after that, it's a terrible mark. Not sure what I was thinking. After that, it's going to be t. So it'll start at t equals 2. So we're going to have 0 up to here, and then from then on, it's going to go up. And so this is our function f of t. How can we write this as using Heaviside functions? Well, this one's really simple, actually. F of t in this case will be equal to t times h of t minus 2. All right, basically this Heaviside function just cuts off until whatever the number is. It cuts everything down to 0, until it gets to 2. Then it just lets the function be itself. Right? So in order to use the functions that we have, though, we want to have the shift, we want to have this t match up with the t minus 2 inside. So we can do that by a little bit of algebraic manipulation. So it's going to be h of t minus 2 times t. And now what I'm going to do is just subtract a 2 and add a 2, just to get things to match up. So nothing has changed there. And now I can write it as h of t minus 2 times t minus 2 plus 2 h of t minus 2 times 2. So the inverse Laplace transform of f of t will be equal to, sorry, the Laplace, I'm doing inverse. The Laplace transform of f of t will be equal to the Laplace transform of h of t minus 2 plus the Laplace transform of h of t minus 2 times 2. And remember, all that means is we need to find, this is the shifted version of the function t here. This is just the shifted version of the function 2 here. So we just need to write down the Laplace transforms of these and multiply by the appropriate exponentials. So we have, in this case, it will be e to the minus 2s times whatever the Laplace transform of t is, that's 1 over s squared, plus e to the minus 2s times whatever the Laplace transform of 2 is, and that's 2 over s. So we have our result. That is the Laplace transform of that function. Now, if you are unsure of this or you don't quite see it happening, I would recommend going back and just calculating this thing, right? Calculate it the old-fashioned way, do the integral, and see that this function is exactly the thing that you actually get. So it matches. It's just this is a different way of getting it. We're getting used to these tools because in certain situations, this is a much easier way, although it doesn't seem like it at first. It turns out to be an easier way to calculate these things than actually doing the direct integrals. All right, one last example. 3 parts now. So this function is equal to t, and then 2 minus t, and then 0. So again, let's take a look at the graph. Oop. Try to be consistent here. Take a look at the graph. From 0 to 1, it's equal to t, so it just goes up to 1. Right? And then from 1 to 2, it's 2 minus t, so at 1 it's 1, and at 2 it's 0. So it is a line coming down here, and then afterwards we have that. All right, so I put it in the right color, down, and then flat. That's our function. All right, can we write this in terms of Heaviside functions? Well, it's a little bit challenging because we're going to have to take 3 different graphs and put them together somehow to figure out what we have here. So let me just try and give a visual picture of what we need to look at. We have 3 functions. We have the function t, and we have the function 2 minus t, so that would be like this one. So let's change colors. So this is t, and this is 2 minus t. And somehow we have to put these things together in order to make sure everything works out. So we're going to let this function be t for a while, but then we need to cancel that out and put in instead 2 minus t. And then after a while, we need to cancel that out as well. That's the idea of what we're going to do here. So how does that look? Well, here's the idea, and have a look at it and make sure you follow along. So we start with t times h minus t. That's going to be the beginning of this function. No involvement from 2 minus t. And then after a little bit, that needs to get subtracted away. So after 1 unit, we need to subtract out t. So t times h of t minus 1, we need to subtract away. That gets us to, that takes care of the first section here just this. And then it would be 0 after that. So we need to add in the downslope starting at t minus 1. So we get plus 2 minus t times h of t minus 1. Right? And then, so that's going to get us, that's going to make our function look like it's going to go up, and then it's going to start going down, and it's going to keep going down. We need to get rid of that last downward bit there. We do that by subtracting this away, again, starting at time 2. So we get, finally, minus 2 minus t h of t minus 2. Whew. But altogether, that will make a graph like that first blue one that we had there, piecing all the pieces together. So let's simplify this a little bit if we can, and it turns out that things work out pretty nicely if we do. We end up with t times h of t, and then for the ht minus 1s, we have this and this, so 2 minus t, we put that together, we get minus, let's just do plus 2 minus 2t h of t minus 1. And then finally we have, for the t minus 2, we have minus 2 minus t h of t minus 2. All right, so this works out great, because what do we have? We have t h of t plus, or let's do minus, so everything lines up, minus 2 times t minus 1 h of t minus 1 plus, I'm going to change the signs again, t minus 2 h of t minus 2. So if you notice, here we have t, here we have t minus 1, and here we have t minus 2, t minus 2. These all match up great. So if we want to take the inverse Laplace transform now, it's in the perfect form for using the formulas that we've had. So f of s will be equal to, well, from this first one, we're going to get 1 over s squared, right? It's just the Laplace transform of t. And now we're going to have minus 2, and this is going to also be the Laplace transform of t, but now it's shifted by 1 unit, so it will be e to the minus t over s squared. And then finally, we have shifted over by 2, so e to the minus 2 s over s squared. There's our Laplace transform. Right? And you can almost read off of this what the function that this is the Laplace transform of. These exponentials tell you that new things are happening. So this basically says, hey, linear function going up at slope 1. And then after 1 time unit, you reduce the slope by 2. So now it's going down with a slope of negative 1. And then after the second time unit, you increase the slope by 1 again. And so it's flat. So it goes up 1, down for a unit, and then flat. So you can kind of start to see what it is that the Laplace transforms are telling you about the original function, although they're telling you this in a very strange language. Right? So it's pretty hard to understand until you've got a lot of experience with it, which is what we're trying to build up now. So go back and look at these examples. Make sure you understand how that Heaviside function is being used to piece together pictures of graphs of functions, and try to do some of these yourself. There are plenty of examples in the book.